Hello, Assalamu alaikum. Today we will talk about this hybridization, and it is the segment of AS level chemistry chemical bonding. So what is hybridization? Hybridization is actually when you have different orbitals. For example, if we have this s orbital, okay, we have this p orbital on x-axis, right? We have this py orbital, this p, but available on y-axis, okay? And suppose if we have the last one on the z-axis, it is the p orbital but available on this z-axis. Okay. So when these different orbitals, when they intermix together, intermixing mean actually there is energy distribution. It is hypothetical concept, and according to this, like now these orbitals they will intermix together and there is energy distribution among these. So you can see here we have this S lower in energy, Px, Py, Pz, they are higher in energy with respect to S. Okay. So when orbitals of different energy, different shapes, when they intermix together, okay, then they intermix together, then they produce equivalent amount of hybrid orbitals. Equivalent mean, for example, you have 1, 2, 3, and 4. Four number of orbitals are intermixing. So the number of new hybrid orbitals, they will be the same as the number of orbitals they are mixing together. So now I will get four new orbitals. Number 1, number 2, number 3, and number 4. Because before mixing, they are 4 in number. So the after the mixing, we will get 4 in number. Okay. So before mixing, you people can notice their shapes are different. It is spherical in shape. It is dumbbell shape. Okay. Before mixing, their energies are different. But after mixing, they will have number 1, same shape, and they will also have same energy. Before mixing, they have different shape, different energy. Okay. Now because there are 1s and 3 orbitals, it is the reason it is known as sp3 hybridization. sp3 mean when 1s and 3 orbitals intermix together and produce 4 sp3 orbitals. So here we have these. They are actually known as hybrid orbitals. Okay, hybrid orbitals. And each one has the character of S, Px, Py, and Pz. So we can say this one has the character, it is also actually a sp3 hybrid. Same thing, it is also sp3 hybrid. So each one, this is also sp3, and it is also has the characters of all these three, okay? All these four, 1s and 3. It is an introduction of what is hybridization. Okay, when orbitals of different shape, different energy intermix together, and then they produce orbitals of the same energy orbitals. Okay, there's another term in your syllabus. They are known as degenerate orbitals. Degenerate orbitals. How to define them? Orbitals having same energy but different axes. Orbitals orbitals having same energy, having same energy. If orbitals they share same amount of energy, they are known as degenerate orbital. Okay? Right. Even you can write this orbitals having same energy but different axes. For example, p, x, py, pz, all the three they are available on the different axes, but their energy is same. Okay. So the next topic is how can we figure out their bonds and okay. So on the basis of bonds, there are two type of bonds, And one of the bond is known as a sigma bond, sigma bond, okay. And other type of bond is pi bond. Before proceeding, we people should know about these two types of bond: sigma bonding and pi bond. Okay. So sigma bond, first bond, whenever you are making any covalent bond, and keep in your mind, we are not talking about any ionic bonding. These are the sequels of, these are the like further sequel of covalent bond only. Okay. So sigma bond, number 1 point for sigma bond is first bond, whenever you are making any covalent bond, your first bond will be a sigma bond always. Okay. First bond is, first bond is always a sigma bond. Okay. Number 1 point. Number 2 point, sigma bond is a strong bond. Sigma bond is a, it is a strong bond because it is formed when sigma bond is formed through head to head overlapping. Okay. When head to head, when orbitals are like overlapping head to head, form through through head to head overlapping. Okay. Head to head overlapping. Okay. For example, we have this px, it is x-axis, and we have, okay, sorry, where is the razor? Here I have this razor. So it is one of the px, and now it is overlapping with another px, for example. And you people can notice there actually there is like a head to head approach. Okay. And we will get this type of chemistry when they will overlap with each other. So you will get the result, like it will, it will like bubble up the thing. Okay. And we will get like this. Okay. So when head to head approach is there, it is sigma bond. And keep in your mind, S will never make a pi bond. S, for example, if we have this S, okay, orbital, and it is overlapping with this Y. When S and Y, S never make a pi bond. S always it will make a sigma bond. Okay, so we will get this. For example, this is the resultant, a bigger one and the smaller one. Okay. So this type of bonding is actually known as the sigma bond. First bond is always a sigma bond, and it is a stronger bonding because there is head-on-head approach. Okay. And other points about sigma bond. So what was the next point of sigma bond? S orbital, S orbital only make a sigma bond. Okay. Always make a sigma bond. I hope you people understand a little bit about sigma bond. Okay. And what about this pi bond? Let me draw a line for their differentiation. Okay. So pi bond is actually a weak bond. Pi bond, pi bond. Weaker mean it is reactive. Sigma bond is stronger but less reactive. Pi bond is weak. It means it can react easily. Okay. Pi bond is weak bond is a weak bond. A weak bond. When a pi bond is formed, there is like parallel approach. When orbitals parallel, or you can say like side by side, when they overlap with each other, then we get this pi bond. For example, we have this carbon and we have this another carbon. Okay. And now one of the bond, it is approaching head on head. When this head on head approach, they are making, this is a sign of sigma bond. Okay, it is a symbol of sigma bond. But suppose if you have some orbitals, they are in this way, perpendicular to the axis. When orbitals are approaching side by side, okay, when they are approaching side by side, they will develop this pi bond. It is a sigma bond, head on head approach, okay, strong bond. But when there is side on side approach, they are known as the pi bonding, okay. And another thing, for example, when there is a carbon, two carbon this bond, these are like sigma bond, okay. And you people can notice it is a like plane is passing from here, and you people can notice this sigma bond, their electron density is on the plane, okay. But in the pi bond, the electron density is above the plane, and even you can say it is below the plane. So that's why, for making idea more clear, we can write this like this cloud is pi electrons density above the plane, and even you can say below the plane. Okay, electron density in pi bonding is higher above the plane and below the plane. Okay, and it is the reason pi bond is weaker because they are overlapping side by side, and this is a weak overlapping. When there is a weak overlapping, they are easy to react. Okay, so the next thing is, for example, now how can we understand? Now how can we inculcate these sigma bonds and pi bonding in our topic hybridization? Okay. So what is sp3 hybrid? We were talking about this sp3 hybridization. sp3, okay. For example, now we are taking the example of CH4. We have this methane molecule, and we will figure out how this carbon is making sp3 hybridization and how a student can understand. Okay. So first recall in your mind what is hybrid sp3. sp3 mean we have one s and we have three p orbitals. For example, we have this px, p orbital available on the x-axis. We have this py, and the end we will have this pz orbital. Okay, it is s orbital, it is px, it is py, and it is pz. Okay, so when these 1s and 3 orbitals intermix together, we will get 4 hybrid orbitals. Here we have this orbit number 1, 2, 3, and we have this number 4. Okay, so in carbon, in CH4 molecule, for example, I have this central carbon 1, 2, 3, 4. I have 4 sp3 hybrid orbitals. So here I am drawing this sp3 number 1, it is sp3 2, it is sp3 3. It is actually not on the plane. They are three-dimensional in structure. Okay, it is the third sp3 hybrid. Okay, fourth one, sorry. So we know like each carbon is connected with 4 hydrogens. Okay, and hydrogen has, for example, hydrogen, it has only one electron. And what is electronic configuration of hydrogen? 1s1. There is only one electron in s orbital, and you know s are in spherical in shape. So now s is overlapping with sp3. Okay, it is sp3, it is sp3 overlapping with s orbital. Okay, and same thing here, we have another hydrogen, third hydrogen, and we will have this fourth hydrogen. It is head on head approach. Okay, so the type of hybridization we can say it is s, it is overlapping with this sp3. Same thing here, you can write it is s and it is overlapping with p3, and here we have this sp3, it is making a covalent bond by overlapping with s. So I hope you people get a little bit idea about this. So if I draw the raw structure, for example, like this, I have the carbon, I have one hydrogen here, I have another hydrogen here, and I have here. Okay. So important thing is their bond angle. So the bond angle is actually the angle between adjacent bonds, okay, close nearby bonds, okay. So these are the two closest nearby bonds. So the bond angle between it is 109.5 degree. Okay, you people have to memorize it. Okay, the bond angle in sp3 hybridization is 109.5, and what's the geometry? It is the bond angle. And if we talk about the geometry or shape of the molecule, it is actually tetrahedral in shape. Tetra mean four, hedral mean corners. Tetrahedral. Okay, here we have this tetrahedral in shape. Okay, so for example, if we have given some question, now we have to identify their sp3 hybridization. For example, I'm randomly drawing this question. Here we have this carbon connected with this here. Here I have this carbon triple bond with N. So how many carbons are there? We can notice there are three carbons. Okay. For example, I have this carbon A, this carbon is B, and this carbon is C. And now examiner is asking, we need to predict the type of hybridization in A, B, and C. Okay. So you people keep in your mind. This carbon is connected with four things. Number one, this hydrogen. Number two, this hydrogen. Number three, this hydrogen. And number four, this carbon. So this carbon is actually further connected with four things. Whenever you see a carbon is further connected with four things, it means that carbon is sp3 hybridized. Okay, so this carbon is actually sp3 hybridized. Understand? Now see on this carbon. This carbon, although it is making double bond, it is connected with one atom of oxygen. One, two, and it is connected with this three carbon. So this carbon B, it is connected with three other elements. Number one, oxygen. Number two, carbon, and three. Whenever you see a carbon is connected with three other things, it means that carbon is sp2 hybridized. It is sp2 hybrid. Okay. And if you look at this carbon, it is connected with two things. One of the thing is nitrogen and other thing is carbon. It is just direct connected with two things. It is sp hybridization. Is sp. Okay. For example, if I have this molecule, I have this C₂H₄, and this is a negative charge. And now you people will say, sir, because it is connected with three things. For example, how? Now it is a carbon, and it is connected with one hydrogen, second hydrogen, and the third hydrogen. Negative charge mean here we have some lone pair of electron. Okay, it is the lone pair of electron. Okay, so I do agree. Like carbon is connected with three elements, three hydrogens, but still here we have two lone pairs. So now you will consider these lone pairs like some element. Okay, now you will consider it is connected just like this tetrahedral way. Okay, in this case, this carbon is also a sp3. If you notice there is some lone pair, not single electron. I'm talking there's a lone pair of electron, okay? Not a single electron, okay? It is also a type of sp3 hybridization. Okay. So now we will talk about sp2 hybridization and we will solve some examples of sp2, okay? So for example, sp2, sp2. So it means we have one s, we have one s, 2p. For example, we have px, we will have this py, here we have this py, and here I am drawing with this yellow color the pz. There's a reason why I'm drawing this with yellow color. Z on z-axis. Okay, s orbital, it is px. Really sorry. We have this px, we have this py, and here we have this pz. Okay, So he is talking about sp2. It means that when one s and now two p's are overlapping. What about pz? It will remain unhybrid. It means PZ is not taking part in hybridization. And here we notice this. Someone is calling me, sorry. Here we notice this S. Here we notice this S, PX, PY, PZ. They were intermixing and we were getting four hybrid. But now S, PX and PY, now they are actually overlapping. PZ is not taking part. So now how many new hybrid orbitals we will get? 1, 2, 3. If 3 are intermixing together, we will get 3 new hybrid orbitals. 1, 2, and 3. So what about this PZ? It will remain unhybrid. It will remain, I'm drawing this as an unhybrid. Okay. So these threes are actually hybrid orbitals. They are hybrid with same energy. And this one is actually PZ, and it's not taking part this intermixing, and it is unhybrid form. Okay? Unhybrid. Okay. For example, now let me make some example. I am drawing this a carbon, and here I have a carbon. Okay. So how many hybrids are there? 1, 2, and 3. So I'm drawing the hybrid number 1. It is hybrid number 2, and it is hybrid number 3. Okay. I have another carbon. It is hybrid number 1, hybrid number 2. It is hybrid number 3. Okay. So still we know each carbon there is a one unhybrid pz orbital, this one. So I am drawing this pz here with this yellow color. So this hybrid orbital is actually unhybrid. Okay, it is unhybrid. Okay, so it is making like sigma bond head to head on approach. Here it is like overlap with this hydrogens, this hybrid orbital. It is overlapping with this hydrogen. Here it is also with hydrogen. Okay, it is the structure of ethene actually. Ethene. When there's carbon to carbon double bond, I think you people learn about this in O levels. For example, it is ethene, carbon to carbon double bond, and further they are connected with these hydrogens. Okay, like this. Okay. So this is a sigma bond, and one of the bond is a pi bond, and all these bonds are sigma bonds. Okay, sigma bonds and sigma. So here we can see it is sp2s bond because this orbital is sp2. It is sp2 bond with s because it is s. Okay, and here we have this s, and this s is making a bond with this sp2. Okay, just like this and this. Okay. Now what about this? It is sp2 bonded with overlapping with sp2. Okay. So what about this unhybrid which is available on each carbon? This unhybrid bond is actually making a pi bond. So now you people I hope understand pi bond is responsible of unhybrid orbital. Okay, we have this unhybrid orbital. So there is now side to side overlapping. If I see, we can see it is side to side or side by side overlapping. Okay, and this side by side overlapping making a pi bond. Okay, first bond is always made by sigma bonds. They are stronger bond because they head on head approach. When there is parallel approach, when orbitals are like parallelly approach together, it is a pi bond, and pi bond is caused by unhybrid orbitals. I hope you people understand this. Okay, so it is sp2 hybridization. Now you can notice this carbon is connected with three things: one hydrogen, second, and this carbon. Okay, so when this carbon is connected with three things, 1, 2, and 3, so this carbon is sp2. Same thing for this carbon, it is connected with one this hydrogen, this carbon, so it is also sp2. And another point which is important for you, if we talk about the geometry of this molecule, this unhybrid orbital is not part of the geometry. If we talk about geometry, it is trigonal, only this hybrid to this and from here to here. Whenever you talk about the geometry of the molecule, its geometry is trigonal. Geometry is trigonal, and the bond angle is 120. Bond angle for sp2 is 120. Whenever you discuss their geometry, we will never suppose we will never consider this unhybrid p orbital. Okay, it is pz, it is also a pz. It is not the part of geometry. We will not involve this in their bond angle. We will just talk about this hybrid. It is making trigonal, and from here to here it is also making a trigonal shape. Okay, the next example, sp hybridization. Next page. Okay, today we are talking about sp hybridization. Okay, sp mean now we have this s, we have this px, we have this py, and now we have this pz. Okay, sp mean one s and one p. Okay, when s and p, like it is px, it is py, and it is pz. When 1s and px combine intermix together and produce two hybrid orbits, the hybrid one, it is another hybrid. So what about px, py? They will remain unhybrid. Okay, they will remain unhybrid form like this. It is py and it is pz. Okay, so now there is possibility of two pi bonds because py is unhybrid as well as pz is unhybrid. Okay, we have two hybrids. Now let me draw the shape. Okay, for example, I'm drawing a shape of this molecule. I have a carbon reactive with this carbon. Okay, it is one hybrid. Here we can say one hybrid. It is another hybrid. Okay, for this first hybrid and second hybrid, and overlapping with this hydrogen and overlapping with this, I'm drawing actually ethane molecule. How to make ethane molecule? The carbon triple bond with other carbon with one hydrogen and other hydrogen. Okay. So now I have to make these py and pz. So I'm drawing py with this yellow color. It is the like py. It is py, and it's also like py. And what about pz? I'm drawing with pz with this color. This is a pz. Okay. So what's the geometry of the molecule? I told you we will never consider these pi bonds. Okay. So it is making a linear geometry. Making a this linear geometry. You can notice it is making linear molecule, because in hybridization and bond angle we only consider hybrids orbitals. Okay, we will never consider this. So now carefully, this yellow like make a bond with this yellow one, this yellow overlap with this yellow, and red one will overlap with this red one. Okay, yellow will overlap with this yellow and red will overlap with yellow. Okay, so you will get this a pi bond and a pi bond, and the middle you will get this sigma bond. Okay, so let me make it more clear for you. I have this carbon and I have this carbon, and it's a first bond and it is a second, and it is actually sp overlap with sp. Okay, so when it is overlapping with this hydrogen, I have this sp, it is overlapping with s, and here I will have this s, it is overlapping with sp. So what's the bond angle? You can notice the bond angle is 180. Bond angle, it is 180 degree. And what's the shape of this molecule? It is linear shape. Okay, it is linear. So now we will draw unhybrid orbitals. What are unhybrid? Px and py. So here I am drawing this py and py. They are overlapping together side by side. And here I am making with pz. Should I draw it here? I will draw it like this. pz overlapping with pz. They are connected together. Okay, so it is a little bit idea about hybridization. In the next video I will extract some mcqs and theory questions, and then I will teach you how can the figure out exact hybridization. Okay, thank you. Goodbye.